Welcome. Today, we're exploring the CAP Theorem, a cornerstone of distributed systems design. Proposed by Brewer in 2000, this theorem fundamentally shapes how we build resilient, scalable systems like databases and caches. Think of it as the rule of thumb engineers use when designing services that run across multiple servers. By the end, you'll understand why trade-offs are unavoidable and how giants like Netflix or your bank make these critical choices. Here's the core idea: you can only pick 2 out of 3 guarantees in any distributed system. Specifically, consistency: all nodes show the same data. Availability: every request gets a response. Partition tolerance: the system survives network failures. Why does this matter? Because networks will fail, messages get delayed or lost. So architects must sacrifice one property when partitions happen. This isn't theoretical, it impacts databases, cloud services, even atoms. Let's break down consistency. Imagine you check your bank balance at 2 ATMs simultaneously, they must show the same number. Technically, every read operation returns the most recent write. Without consistency, you might withdraw cache based on outdated data, leading to overdrafts. Systems like financial databases enforce this rigidly, but it comes at a cost we'll see later. Availability means the system always responds even if it's not the latest data. Picture an ATM during a network outage. It might give you cache based on yesterday's bound stale data, but it won't display an error. Trade-off: you get functionality now but risk inaccuracy. Social media apps prioritize this. You can still post during outages, even if feeds lag. Partition tolerance is non-negotiable in distributed systems. If a network cable gets cut or a server crashes, the system doesn't collapse. Think of atoms. Even if the central bank's network goes down, local machines might still dispense cache using cached data. Why is this mandatory? Because partitions aren't if but when in real-world networks. Here's the trilemma. CAP forms a triangle where choosing 2 properties forces sacrificing the third. For example, pick consistency plus availability CA. You lose partition tolerance. Pick consistency plus partition tolerance CP. Availability suffers. Pick availability plus partition tolerance AP. Consistency weakens. This isn't just theory, it's the blueprint for every distributed system design. CA systems consistency plus availability are rare. They work flawlessly until the network fails. Example: traditional databases like PostgreSQL on a single server. All reads/writes are consistent and fast, but if the network partitions, the whole system stalls. That's why Kingsbury jokes there are no CA systems, only CA fantasies. Real distributed systems need partition tolerance. CP systems prioritize data correctness over uptime. Banks use these. If a transaction can't verify across all nodes, e.g., during a partition, it rejects your request. Tools like MongoDB or ZooKeeper work this way. You'll see errors like system unavailable, but your balance stays accurate. Sacrificing availability here prevents financial chaos. AP systems keep running no matter what, but may return outdated data. Social apps like Facebook use this. Your post goes live instantly, availability, but followers might see it late in consistency. Databases like Cassandra or DynamoDB embrace eventual consistency. Data syncs after the partition heals. Perfect for non-critical systems where speed, precision. Critical insights. Partitions are unavoidable, so all real systems choose P plus either C or A. PACELC refines CAP. During partitions, P, trade availability vs consistency. In normal operations, E, trade latency vs consistency. Example: no partition? A system might optimize for fast responses, low latency with strong consistency. This is why CAP is just the starting point. Let's map theory to practice. Cassandra AP. Netflix uses it. Streaming stays up, even if recommendations lag. Kafka CA prioritizes data consistency, may pause if replicas fail. ZooKeeper CP becomes read-only during partitions used for coordination in Hadoop. Cosmos DB flexible. Per request tuning, e.g., charge my card now equals strong consistency, show my order history equals eventual. To wrap up, all distributed systems start with partition tolerance P, then choose C or A. CA is a myth for distributed architecture, single node only. AP eventual consistency powers social/media Netflix. CP strong consistency protects money/inventory. Remember Brewer's wisdom: CAP forces conscious trade-offs. Designers ask, what can my users tolerate errors, delays, or stale data? That answer shapes everything.